Unreal places, Earth's greatest natural spectacles. Bottled lake. Water stays pink. Ice 800 meters thick has retreated 3 kilometers. The forces behind such spectacles also close routes, revealing where human access reaches its limit. That limit is set by rock, water, heat, wind, and ice, not by the reach of a camera. I want to test a familiar assumption, that cinema must enlarge reality to make it spectacular. But a lens can only frame forces already working at continental scale. People answer with cliff paths, mountain railways, thermal plants, and settlements locked to steep ground. Even then, rockfall, weather, and heat can stop passage. In this film, we explore where the planet outperforms fiction, how human engineering enters the frame, and why the greatest spectacle remains beyond human control. An island lake holds a color that looks manufactured, even after its water is lifted into a bottle. Lake Hillier stretches roughly 600 meters on Middle Island, with only dunes and paperbark woodland separating its pink basin from the dark blue Southern Ocean. The color is not a reflection staged by angle or weather. In this highly saline water, salt-adapted organisms, including Dunaliella salina, pigment-producing bacteria, and archaea, likely create the hue. That chemistry defeats the easy explanation. The lake does not merely catch pink light, its water carries the color. Matthew Flinders recorded it in 1802 after climbing the island's highest point, then named it for crew member William Hillier. Salt was briefly harvested here in the 19th century, but distance prevented lasting industry. That distance still limits access and preserves the shore. Middle Island has no regular public access, so most views come from scenic flights near Esperance. Altitude is the only way to read the landscape as one unit. From above, pink water, white sand, green woodland, and blue ocean fit within a few hundred meters. A color grade would add nothing. Distance both reveals the lake and keeps most people from its shore. Day by day, the Alps' longest glacier deforms under its own weight, moving only fractions of a meter while stretching more than 20 kilometers. The Aletsch Glacier is the longest in the range, and at Concordiaplatz, its joined ice streams form a mass more than 800 meters thick. Gravity drives that mass downhill, not as a visible rush, but through slow deformation. Its daily movement is small, but pressure continues through the entire frozen mass. Long, dark bands, called medial moraines, mark where separate glaciers have merged. They are not decoration. They trace the direction of travel across the frozen corridor. Crevasses open where the ice bends, accelerates, or drags across uneven bedrock. Every fracture records pressure inside ice that appears motionless. That apparent permanence is the deception. Measurements beginning in the 19th century record more than 3 kilometers of retreat, along with major thinning. As the margin withdraws, bare rock emerges, slopes lose support, and meltwater changes course. The glacier tongue now sits farther up the valley. Eggeshorn and Bettmerhorn offer rare views over almost the entire length. Reaching that perspective turns human access into a measured encounter with altitude, distance, and moving ice. Only the widest frame reveals the contradiction. Nature still overwhelms the image, even as the Alps' longest glacier loses ground within it. At Perito Moreno, an advancing ice front can close a lake channel and force the water to carve its own escape. Across more than 7,000 square kilometers of Argentine Patagonia, Los Glaciares National Park protects dozens of glaciers fed by the southern Patagonian ice field. Those glaciers do more than feed the lakes. They grind rock into fine flour, turning the water an opaque turquoise. In the north, granite spires rise around Fitzroy, above forest and Patagonian steppe. Farther south, enormous arms of Lago Argentino receive ice moving out of the Andes. Perito Moreno is the park's most accessible ice front, and it has behaved more steadily than many neighboring glaciers. Even here, position and thickness continue to vary. When the glacier presses against the Magallanes Peninsula, it can obstruct a channel of Lago Argentino. Water rises behind the barrier until pressure excavates a tunnel through the ice. An arch forms above the opening, then gives way through a sequence of deep fractures. The timing follows no performance schedule. Buoyancy, stress, water temperature, and glacier movement decide it. The camera can only wait and record it. Pressure, moving ice, and rising water produce a scale no visual effect can command. These cliffs began as tropical reefs, yet now rise more than 3,000 meters above northeastern Italy. More than 250 million years of uplift, ice, frost, landslides, and running water turned seabed into a saw-toothed skyline. Magnesium-rich carbonate, hardened beneath an ancient sea, rose with the Alps, then split into isolated towers, pinnacles, and vertical walls. UNESCO protects 9 Dolomite mountain groups, each recording a different result of the same immense reshaping. Frost and rockfall still break their edges. Then low sunlight reaches the pale stone. Yellow deepens into orange. Orange shifts to rose, and Trecime di Lavaredo carries the change across entire cliff faces. The effect is called enrosadera. It depends on pale rock, low light, and a narrow window of clear sky. No color grade can improve it. Human access has never erased the mountain's terms. During the First World War, crews cut paths and tunnels, fixed ladders, and rigged protected climbing lines through this exposed frontier. Many became today's Via Ferrata network. Cable cars and roads shorten the approach, but sudden storms, snow, rockfall, and open traverses still decide when movement stops. At dusk, real limestone turns rose for only as long as clear sky and low light permit. The mountain, not the camera, sets the window. A mountain more than 5,000 meters high carries colors that can strengthen, fade, or almost vanish as weather shifts. They are tilted sedimentary layers exposed over geological time beside Gate in Peru's Cusco region, not pigments added to the surface. Iron-rich minerals drive the reds and browns. Clays and other mineral combinations produce pale yellow, greenish, lavender, and gray zones across the slope. The palette is real, but never fixed. Sunlight sharpens one band, cloud shadow mutes the next, while moisture, frost, and snow can change the whole slope. That instability is what effects struggle to copy. The mountain does not present a finished image. Light keeps rebuilding it. Access adds another hard limit. The ridge stands above 5,000 meters, where cold, wind, and thin air can slow people accustomed to Cusco's lower elevation. Local Quechua communities manage access, sell food and crafts, and provide horses when the climb proves demanding. This is not empty scenery. Livelihoods now follow an old herding route. Once photographs spread, heavy foot and horse traffic widened trails and pressed fragile high-altitude soil and grazing land. From above, the mineral bands outmatch any digital palette, while widened ground below records the price of access. Rain and snowmelt travel through hidden limestone before reappearing as a fall nearly 600 meters high, or dispersing into mist. Serengeti Falls drops in 3 stages above Lake Whalen, but its strength depends on rain and snowmelt moving through hidden limestone channels. Water enters fractures on the Terraced Plateau and travels underground through karst. The cliff is only the final release point. In spring, melt, or heavy rain, the flow can spread into a broad white torrent. In dry periods, parts narrow to a thread or break into mist. The middle fall carries the main shock of scale, roughly 300 meters through open air before meeting the lower cliffs. No constructed stage needs that much vertical space. Near the base, another force enters. The Rinquel spring pushes directly from a cave, and its discharge can rise quickly when precipitation feeds the drainage network above. Hidden drainage makes each rapid increase appear to push straight from solid rock. Paths from Betlis bring visitors close, but hidden drainage still decides whether they meet a torrent, a thread, or mist. The lake alone reveals the entire descent. Scale emerges when the eye follows the water from karst plateau to lower forest, a continuous descent too large to grasp from the path alone. A geothermal power plant produced one of Iceland's most convincing visions of an alien world. At Svartsengi, fluid rises from about 2 kilometers underground at nearly 240 degrees Celsius before its heat is harvested for energy. This was never a natural bathing lake. Cooled discharge spread across porous black lava, where silica gradually sealed the ground and trapped the flow. Suspended silica also scatters light, giving the water its milky blue color beneath an overcast sky. What appears unreal is mineral physics. Managed flow keeps the bathing areas near 38 degrees Celsius and continually renews the water. Engineering maintains the image, but geology supplies its force. Cold air crossing the warm surface drives steam upward. Lava walls vanish and return, not through visual effects, but through a hard temperature difference. Slow motion does not exaggerate steam, it exposes the mechanics. Heat, minerals, air, and lava build the image in real time. Yet renewed volcanic unrest across the Reykjanes Peninsula has forced periodic closures. Tourism and power infrastructure occupy ground that still shifts under volcanic pressure. The Blue Lagoon is an unstable bargain between industry and nature. No fabricated pool can match a color maintained by machines, yet commanded by the earth beneath them. A river helped build dunes more than 300 meters high, yet those dunes now block another river from reaching the Atlantic. The Namib Sand Sea has persisted for tens of millions of years, while the Sorchab ends inside it whenever sand closes the route west. Much of this sand began far south as sediment carried toward the ocean by the Orange River. Coastal currents moved it north. Prevailing winds drove it inland. Time sorted the grains and oxidized their iron-bearing minerals, deepening older sand from orange to red. The color records age, not digital grading. The ridges never settle. Wind pushes grains up one face. Gravity slides them down the other, rebuilding each sharp edge. Exceptional rain can still force floodwater across Sossusvlei's clay basin. Shallow pools appear briefly, then evaporation returns the pan to dust and salt. At nearby Deadvlei, shifting dunes cut camel thorn trees off from floodwater. Extreme dryness preserved the wood, leaving dark trunks fixed against pale clay. Dawn supplies the final mechanism. Low light strikes one dune face, while the opposite side remains in deep shadow, splitting the same ridge into red and black. That contrast must remain hard. No built backdrop can reproduce light this severe across a landscape that wind is still rebuilding grain by grain. One foothold is all the mountain allows, wooden boards fixed directly against a granite cliff. Mount Hua's south peak reaches more than 2,100 meters, and 5 principal summits are linked by ridges, stairs, temples, and rock-cut paths. That number understates the height. Huashan rises abruptly from the Shanxi Plain, then drops so quickly toward its valleys that open space becomes the main physical force. For centuries, Taoist hermits and pilgrims made the hard ascent part of devotion. Shrines took hold where every load climbed by stone, chain, and ledge. Historic travelers relied on steps cut into rock and iron chains set along exposed faces. Cable cars and improved paths now carry most visitors upward, but the plank walk still concentrates the mountain's full force into boards, cliff anchors, and a modern harness line. Movement alternates between confinement and release. Narrow stairs press between granite walls. Ridge saddles open suddenly, and the valley falls away faster than the eye can measure. Fog can erase that valley, leaving temples and summits above cloud. One human foothold against the granite drop is enough to establish the scale. The valley supplies the rest. Sometimes, the impossible image is the route itself. Across roughly 140 meters, 6 stone arches carry a passenger train about 65 meters above a gorge before it vanishes into an unbroken alpine cliff. Completed in 1902 near Fillesur, the Landwasser Viaduct bends across the gorge and enters a tunnel cut directly through the vertical rock face. The curve lets passengers catch part of their own train, suspended over the river. That brief crossing hides a much larger engineering campaign. The Albula line uses spirals, tunnels, bridges, and controlled gradients to carry ordinary trains through the Alps without conventional rack assistance. Builders used local stone and lime mortar. Tall, tapered piers cut weight while preserving stability, a hard answer to height, gravity, and a restricted worksite. More than a century later, scheduled passenger trains still cross its masonry as part of the UNESCO-listed Rhaetian railway landscape. The decisive image needs distance, not ornament. Train, bridge, cliff, and tunnel must remain together, because only the full view shows masonry forcing a route through mountain rock. For a few seconds, scheduled transport becomes the spectacle. A train crosses century-old stonework and disappears into the mountain that dictated the route. The ground above Gijin gives no warning of the unsupported roofs below. Tight passages open into halls, hundreds of meters long within a cave system running for many kilometers beneath Guizhou. This scale began with mildly acidic groundwater entering joints in thick limestone. Water widened the fractures, while underground streams carried the dissolved rock away. Once those voids opened, mineral-rich droplets started building the interior grain by grain. Calcite formed stalactites, columns, curtains, rimstone pools, and surfaces resembling forests or fixed waterfalls. The silver rain tree makes that slow work measurable. It rises about 17 meters, a slender crystal structure assembled by repeated drops rather than a studio crew or construction crane. Local communities knew of cave openings before a tourism survey in 1980 brought formal exploration. Today, long walkways, stairs, and controlled lighting open only part of the underground network. That restraint matters. Every walkway and lamp must admit visitors without disrupting the humidity, airflow, dripping water, and fresh mineral growth that keep the cave changing. Under the largest roofs, walkways and staircases become thin lines, turning visitors, not decoration, into the measure of Gijin's scale. A basin of fire burns in a desert where even its origin remains unsettled. Roughly 60 to 70 meters wide and about 30 meters deep, Darvaza feeds flames from gas seeps across its floor and walls. The crater lies in the Karakum Desert, around 260 kilometers north of Ashgabat. In daylight, it appears as a scorched depression in a plain. Darkness exposes the energy still escaping underground. The familiar account links it to a Soviet drilling collapse and deliberate ignition in 1971. But no complete public record confirms that sequence, and other accounts place the collapse earlier and the ignition later. What keeps it burning is clearer. Methane-rich gas moves through fractured ground, meets oxygen and enough heat, then ignites at many separate vents. At night, those separate flames merge into one glowing basin visible across the flat desert. No effects crew needs to enlarge it. The uninterrupted fuel supply controls the spectacle. The display consumes usable gas and causes environmental damage. Turkmen authorities have repeatedly considered reducing or extinguishing it, making the crater's future a question of energy policy as much as geology. Darvaza outperforms any staged fire because its fuel, scale, and uncertainty are real. Yet the gas loss sustaining the image may force authorities to bring it to an end. The crisis begins beyond the shoreline. As Lake Urmia retreats, exposed salt threatens farms across the same strained watershed. Since the 1990s, Lake Urmia has retreated under the combined pressure of upstream dams, irrigation withdrawals, repeated drought, and warmer conditions. This is a closed basin, trapped between Iran's east and west Azerbaijan provinces. Water has no route to the sea. It escapes mainly through evaporation, leaving its salt behind. That chemistry once sustained dense populations of brine shrimp. They fed flamingos and other migratory birds across the lake's islands and shallows. As inflow weakened, blue water gave way to pink saline shallows, then broad white crust. Wind can lift salt from the lakebed toward orchards and fields, dependent on the same strained watershed. A causeway carrying the Urmia Lake Bridge cuts between the northern and southern basins. An open bridge section allows some exchange, but the embankment still restricts circulation. Restoration work has tried to return river flow, reduce farm consumption, and reconnect wetlands. Rain and snowmelt can bring seasonal recovery, but they do not erase the longer retreat. The aerial contrast makes the change impossible to hide. Blue water on one side, exposed white salt on the other. No visual effect matches a basin recording decades of retreat in blue water and white salt. What looks like one immense reef is actually a chain of separate habitats stretched along a continent. The Great Barrier Reef runs for roughly 2,300 kilometers along Queensland's continental shelf, linking thousands of reefs, coral cays, and islands. Its builders are tiny coral polyps. Generation after generation, they deposit calcium carbonate skeletons, raising a framework whose living layer occupies only the sunlit surface. Air and water reveal the full scale together. Reef rims and lagoons divide the shelf. Below, coral walls, seagrass beds, and mangroves support more than 1,500 fish species. Currents carry larvae between separate reefs. After a precise combination of season, temperature, and moon phase, synchronized coral spawning releases vast clouds that seed the next generation. This is also sea country for Aboriginal and Torres Strait Islander peoples. Their connections long predate modern tourism. Rangers, researchers, marine zoning, and managed access protect an ecosystem too large to change evenly. Repeated marine heat waves have caused mass bleaching. Cyclones polluted runoff, and crown-of-thorns starfish add pressure, so one reef may recover while another remains badly weakened. No single frame can contain it. Aerial scale and underwater detail must join before the fact becomes clear. Tiny animals built a structure on continental dimensions, and rising heat can alter it reef by reef. A ship entering this corridor is dwarfed by rock above and almost a kilometer of dark water below. Aurlandsfjord runs about 30 kilometers from Sognefjord, between mountain walls rising as much as 1,800 meters, while the deepest water approaches 1,000. Repeated ice ages drove glaciers through older valleys, grinding a U-shaped trough hundreds of meters below today's surface. When the ice withdrew, rising seas flooded the cut. Hanging valleys remained high on the walls, sending rain and snowmelt over the cliffs. Access obeyed the terrain. Farms occupied rare shelves of workable ground, while boats moved people and goods more easily than routes across the mountains. Modern engineering confronted the vertical barrier. The Flåm Railway climbs nearly 900 meters in 20 kilometers, using tunnels and steep gradients to reach Myrdal. Cruise ships now enter water once dominated by local vessels. They bring business to Flåm and Aurlandsvangen, but also congestion and concern over emissions inside a corridor where settlement has little room to spread. From above, farms, roads, trains, and ships shrink into markers between cliff and deep water. That comparison is Aurlandsfjord's real measure. Engineering can gain access, but it cannot make the cliffs lower or the flooded trough shallower. Water falls nearly a kilometer here, yet much of it never reaches the forest as a coherent stream. From Oyan-Tepui, Angel Falls plunges nearly 1,000 meters, including more than 800 meters without a break. Unlike waterfalls fed by permanent snowfields or huge lakes, this flow begins with rain-crossing exposed sandstone. The wet season strengthens it. The dry season can narrow it sharply. Then height takes command. Wind tears the water into spray, and the long descent gives that spray time to drift across the cliff before reaching the trees. Only a view of the full drop makes the physics legible. The river appears to dissolve in open air. The Pemon had long known the falls and surrounding tepuis, using indigenous names including Karapakupai Vena. Jimmy Angel's flights brought wider international attention in the 1930s. Access remains uncertain. Motorized canoes follow the river, then a forest walk carries the route onward. Low water hinders navigation, while cloud can conceal the upper wall completely. Rainfall, river depth, wind, and patience decide whether the whole structure can be seen at once. No ticket or timetable can command those forces. By the forest, gravity and wind have dismantled a river into weather. A flat-topped mountain towers over a modern city, then pours cloud across its own cliffs. Table Mountain rises more than 1,000 meters above Cape Town, and its sandstone plateau runs for nearly 3 kilometers between steep cliffs. City movement continues directly below. Roads, neighborhoods, harbor infrastructure, and the Atlantic coast remain active beneath rock laid down hundreds of millions of years ago. The famous tablecloth is not a visual effect. Moist southeasterly air strikes the mountain, climbs, cools into cloud, and spills down the far cliffs before warmer air strips it away. The shift can be rapid. Strong wind can stop the rotating cableway and quickly make exposed hiking routes difficult. Under that cloud, Fynbos survives on nutrient-poor soil. More than 1,500 plant species grow on the mountain, many with highly restricted ranges. Fire creates a harder balance. Many Fynbos plants need heat, smoke, or cleared old growth to regenerate. Fire returning too often can disrupt that cycle. Invasive plants and expanding urban edges add pressure from below. Protection must manage those threats without removing the fire cycle that Fynbos requires. The decisive image is cloud crossing ancient sandstone above a working city. No studio backdrop can bind weather, geology, and urban pressure this tightly. Switzerland has built a walkway where solid ground ends, but the engineering works only because the drop remains impossible to ignore. At more than 2,100 meters, Grindelwald First stands above the village, reached by a multi-stage gondola through forest and alpine pasture. The first cliff walk fixes steel grating and suspension sections directly to rock. Railings and cables provide security, while open space beneath the platform keeps the valley fully exposed. A straight-down view is essential. It reveals what constructed sets usually hide, not an image of height, but real relief continuing far below the boots. This access is not casual. Lift operators, maintenance crews, guides, and rescue services keep the route working where snow, ice, thunderstorms, cloud, and wind can close exposed attractions quickly. The same exposure that sells speed also limits it. Wind and ice can stop the machinery. At Bakalpsi, even calm conditions are temporary. The water can hold the Schreckhorn and nearby summits until wind breaks the reflection apart. Each season changes the routes. Snow returns the slopes to winter use. Summer opens meadows, carts, and trails toward the lake. Here, steel reaches the edge, but the alpine drop keeps the vertigo physically real. Where the mountain withholds level ground, daily life becomes the route. Balangan grips both sides of a steep valley in Iran's Kurdistan province, where one roof becomes the courtyard and passage for the home above. This arrangement saves the broad streets the mountain cannot provide. Narrow stairs force daily movement straight up and down the slope, while footbridges join the two sides. Stone, earth, timber, and repeated repairs help households withstand winter cold, summer heat, and gravity. These materials keep the settlement attached to the valley day after day. At the valley floor, water reaches deeper soil. Walnut and pomegranate orchards turn that narrow strip into productive ground, tying the stacked homes above to crops below. Kurdish language, clothing, music, and seasonal gatherings keep the shared ground active, even as migration and modern construction change the village. At close range, its logic is daily labor, carrying crops, reaching water, crossing roofs, and maintaining shared ground. From across the valley, those separate acts disappear into horizontal bands. Palangan must be held whole. One continuous mass of stone, shaped by a mountain that left no room for a conventional village. Rain does not hide Milford Sound. It multiplies the landscape. More than 6 meters can fall in a year, feeding permanent waterfalls and producing hundreds of temporary cascades on cliffs around 1,200 meters high. Piopiotahi is not a sound in geological terms, but a fjord cut and deepened by glaciers, then flooded by the sea. That history left near vertical rock where ordinary distances become unreliable. Mitre Peak rises more than 1,600 meters near the fjord. Its scale becomes clear only when a boat passes below, reduced to a small moving mark against the rock. The same water that creates the spectacle also controls access. Heavy rain can trigger avalanches and landslides, closing the alpine road that reaches the fjord through the Homer Tunnel. Below the surface, forest-stained freshwater floats above denser seawater and blocks part of the light. That dark layer lets black coral associated with deeper habitats live at unusually shallow depths. Seals, bottlenose dolphins, and fjord-land-crested penguins use the protected waterway. Their habitat is shaped by the same rainfall that can halt human access. Beneath Mitre Peak, one boat settles the argument. Reality needs no visual effect when 1,600 meters of rock supplies the scale. Here, the settlement is only one layer of a larger working slope. In Uraman Takt, stone houses, terraces, springs and seasonal routes lock village life into the contours of the Zagros. High in the Haraman region of the Zagros Mountains, the village does not flatten terrain. It follows every contour. Covered passages and narrow stairs compress movement into the gaps between walls. The pattern protects scarce level ground and keeps homes close to springs, orchards, and communal areas. Beyond the houses, dry stone walls hold thin soil against frost, rain, and ground movement. Continual repair is essential because a neglected terrace can lose the ground needed for crops. Walnuts, pomegranates, grapes, and other crops grow on narrow terraces. Livestock move between elevations with the seasons, extending village work across the mountains. That working landscape helped earn the Haraman and Uramanat Cultural Landscape UNESCO recognition in 2021. Harami language, music, oral tradition, and the annual Pir Shalia ceremonies keep the stone roots active as communal ground. The full slope reveals a system rather than a monument. Houses endure because terraces, springs, paths, and continual repair still work together. Abyane's famous red is not a fixed facade, it is maintenance made visible across an entire mountain village. Abyane's houses draw their rust-red surface from local earth rich in iron-bearing minerals, joining mud brick, clay plaster, timber, and stone into one dense settlement. The unity looks absolute, but it is not permanent. Rain and winter weather eat into the earthen walls, so the same soil must be applied again by human hands. Houses rise in stepped rows, with rooftops, stairs, and narrow alleys locking the slope together. Small openings reduce heat loss and blunt the force of intense sunlight. This hard architecture also protects a living village. Springs and traditional water channels feed orchards of apples, apricots, and walnuts, where the mountain would otherwise ration every harvest. Inside the Friday Mosque, an 11th century wooden minbar and carved doors preserve the skill of craftspeople from more than 9 centuries ago. The local dialect and traditional dress carry another record that brick alone cannot hold. Residents age, younger people leave, and tourism brings income while pressing on a settlement built for endurance, not display. Abyane needs no manufactured color. Honest light reveals a natural red kept intact by soil, weather, and the labor of continued habitation. For part of the year, the largest salt flat on Earth removes the horizon. Salar de Uyuni spreads across more than 10,000 square kilometers of Bolivia's Altiplano at roughly 3,600 meters. Prehistoric lakes once filled this closed basin. As they expanded and evaporated, they stacked salt, clay, and mineral-rich brine beneath a crust too broad for ordinary visual reference. In the dry season, groundwater rises and vanishes into the thin air. Contraction and salt growth divide the surface into interlocking polygons that continue beyond visible reference points. Then summer rain changes the geometry. A sheet of water only centimeters deep smooths the crust and reflects clouds, vehicles, and distant volcanoes, until ground and sky become impossible to separate. That apparent perfection is physically deceptive. Soft brine and flooded sections can hide beneath the surface, while the loss of landmarks makes careful navigation essential across the immense basin. Former islands rise from the salt, carrying exposed coral-like rock and giant cacti. They mark the vanished lake even when the flat appears empty. Beneath the crust, lithium-bearing brine carries global economic weight, setting industrial demand against water use, local communities, tourism, and slow natural renewal. No studio could build this mirror at scale. Shallow rainwater erases the horizon and exposes the limits of human control. A lake with a pH above 10 holds East Africa's most important regular breeding site for lesser flamingos. Mineral springs can approach 60 degrees Celsius, adding geothermal heat to a basin already concentrated by extreme evaporation. The chemistry begins with confinement. Rivers and springs carry dissolved salts into this closed Tanzanian basin, but no river drains them away. So fierce evaporation concentrates sodium carbonate and other minerals. Salt-tolerant cyanobacteria and other microorganisms answer that pressure with red, orange, and pink pigments. Those colors are not contamination or visual enhancement. They are living evidence of an extreme habitat. The same microscopic life feeds lesser flamingos across East Africa. At Natron, exposed mud and salt islands give their breeding colonies a barrier that many land animals cannot cross. Protection here is never fixed. High water can flood nests. Severe drying can reconnect colonies to the shore or shrink the feeding grounds that support them. Above the basin, Ol Doinyo Lengai adds another chemical exception. It erupts rare nitrocarbonatite lava, relatively cool and dark when fresh, then rapidly altered by weather. The volcano, lake, microbes, and birds share one foundation. Rift geology links the minerals below to the surface color and flamingo colonies above. Set against the flamingos, Natron's true red-orange water makes reality stronger than fiction. No film crew could direct this many bodies across one horizon. More than 1 million wildebeest, joined by hundreds of thousands of zebras and gazelles, move through an ecosystem far larger than the nearly 15,000 square kilometer park. The migration does not obey a fixed calendar. Rain raises nutrient-rich grass, and the herds follow that food across Tanzania's plains and toward Kenya's Masai Mara. Early in the year, many gather on the southern shortgrass plains. Hundreds of thousands of calves arrive within a concentrated period, turning open country into a nursery under constant pressure. As the ground dries, the mass shifts west and north. Around scarce water, loose herds compress into long columns and parallel trails. River crossings tighten that pressure. Current steep banks, crowding, and crocodiles can break the flow in seconds. Predators exploit every disruption. Vultures and smaller organisms return nutrients to the grassland. What appears to be a single surge is also a cycle that rebuilds the ground beneath it. Human lines now press against an inherited route. Roads, lodges, protected area borders, livestock zones, and climate variability can narrow access to widely separated seasonal ground. From above, chaos resolves into fronts shaped by water, grass, fear, and inherited movement. The spectacle survives only if those widely separated seasonal grounds remain connected. Europe's largest ice cap by volume rests on active volcanoes. Vatnajökull covers nearly 8,000 square kilometers of southeastern Iceland, while active volcanoes including Grímsvötn and Bardarbunga remain hidden beneath the ice. Snow piles on the high interior, compresses into dense ice, then flows outward through many outlet glaciers. The cap looks fixed. In fact, gravity is always dragging it toward lower ground. Below, geothermal heat can melt the glacier from its base. Water gathers under the ice until pressure opens an escape route across the outwash plains. These glacial floods can carry sediment and ice blocks with enough force to damage roads and bridges. Human access depends on roads and bridges crossing terrain that can flood without warning. At At the margins, summer meltwater cuts channels that may become deep blue caves in winter. Dense ice absorbs more red light, but the color hides a practical warning. Every passage is temporary. Roofs thin, roots shift, so guides must reassess the glacier each season rather than trust last year's map. At Jökull, ice breaks into Jökulsárlón and drifts toward the sea. As the glacier recedes, the lagoon grows and new terrain emerges. Blue chambers stand above volcanic heat. No visual effect matches Vatnajökull because its ice never stops moving. An object about 50 meters wide opened a bowl more than a kilometer across. The collision came roughly 50,000 years ago, cutting nearly 200 meters into northern Arizona and shifting millions of tons of rock within seconds. Shock waves excavated the crater and overturned rock layers around its raised rim. Most of the iron-nickel body vaporized or fragmented, leaving only scattered pieces across the desert. That missing mass later misled mining engineer Daniel Barringer. He argued for an extraterrestrial origin, then searched unsuccessfully for a large iron body below. The impactor had not remained intact. Yet the search pushed science toward a larger question. Could one planetary collision reshape solid ground this quickly? Later researchers found shocked minerals and other impact evidence. The crater became a field model for reading similar structures on the Moon and other worlds. Apollo astronauts trained here because the desert preserved a planetary lesson at human scale. Ancient force became practical preparation for leaving Earth. Preservation is the other reason the shape remains so clear. The crater is geologically young, and the dry climate has not softened its rim as quickly as wetter conditions would. From above, the bowl is almost geometrically clean. At its rim, that planetary violence contracts to a human lesson. Solid ground can be remade in seconds. A river shared by two nations becomes a moving wall that no water effect can convincingly rebuild. At Horseshoe Falls, most of the Niagara River crosses a curved crest, nearly 800 meters wide, then drops about 50 meters. That water is moving from Lake Erie toward Lake Ontario, through American Falls, Bridal Veil Falls, and the dominant Horseshoe Curve. The falls began after the last ice age, when meltwater drove the Niagara River across hard dolostone over softer rock. Undercutting weakened the ledge and shifted the cataract upstream for thousands of years. That retreat carved the Niagara Gorge. Today, control works divert substantial flow through hydroelectric plants on both sides of the border. Engineers also regulate water by season and time of day. The same river must remain a spectacle, produce power, and surrender less rock to erosion. Boats enter the turbulent basin, while tunnels and overlooks approach the edge. Mist can hide the cliff, but it cannot suppress the continuous roar. The power lies not in height alone, but in uninterrupted mass. Even after diversion and regulation, Millions of liters keep crossing the stone second after second. At Erta Al, molten rock from deep inside Earth remains exposed to the night air. Erta Al rises only about 600 meters above the Afar Depression, where a summit pit has repeatedly held a long-lived lava lake since the early 20th century. This is one of the few places where continental crust is being pulled apart above sea level. Faults open, allowing magma to rise beneath salt flats and bare desert under extreme heat. The lake is never a fixed pool. A dark crust forms, cracks, folds, and slides aside as molten rock circulates beneath it. Gas pressure opens the surface from below. At times, overflow or drainage redraws the crater floor, so the exposed red surface never remains the same. Access depends on AFAR guides, drivers, guards, water, and camps carried across remote ground. Night travel avoids part of the daytime heat and exposes the orange glow, but darkness also hides unstable footing. Volcanic gas, shifting routes, and regional security conditions can stop the approach. The landscape permits no easy schedule and no fixed viewing point. That is why the night image needs no enhancement. No fire effect can match molten rock exposed inside a changing crater. A mountain shared by 3 countries rises as a flat summit sealed behind cliffs hundreds of meters high. Mount Roraima reaches about 2,800 meters near the junction of Venezuela, Guyana, and Brazil, on sandstone approaching 2 billion years in age. The rock is ancient, but water still cuts it. Rain enters cracks, carves channels and pools, then spills over the rim in temporary waterfalls. Cloud can reduce visibility to a few meters. Wind and constant rain grind across dark rock, exposed ground, and nutrient-poor soil, continually reshaping the plateau. Isolation supports specialized plants, including carnivorous species and animals with restricted ranges. The summit is not completely sealed, but its cliffs remain a hard biological barrier. For Pemon communities, Roraima carries meaning beyond geology. The usual route from Venezuela requires several days across savanna and wet summit ground under persistent rain. Access depends on a natural ramp through one break in the walls. Everywhere else, cliffs make human entry answer to the mountain's shape. At a boundary marker on the summit, 3 modern states meet on rock, approaching 2 billion years old. The final perspective is humbling. People can name and cross this plateau, but its cliffs, weather, and isolated life still set the terms. I began with a test. Could the real planet still exceed the images built to imitate it? The answer is not color alone. It lies in scale that defeats a lens, motion that cannot be reset, and pressure that forces roads, bridges, settlements, and bodies to adapt. Cinema can copy the surface. It cannot command a glacier, hold a desert, or schedule falling water. That distinction matters now. Many spectacles are shifting under rising heat, mining, and heavy visitation. The harder humanity pushes into them, the clearer their limits become. I take away a blunt lesson. Nature still exceeds every production, but these landscapes are not permanent sets. The power of this age will be measured not only by what civilization can reach, but by what it has the restraint to leave intact. Continue with this series as it tests the world's most impossible-looking places against the limits of cinema, and examines the restraint required to keep reality greater than the imitation.